Yes, children, welcome back to Chemistry Wala classes. This is Satish Kumar. In this video, I am going to talk about hybridization, very important topic for class 10th and intermediate students from chemical bonding lesson. So first of all, I will give you definition. Before going to definition, hybridization concept given by Linus Pauling in the year of 1931, and he's from USA, United States of America. So first of all, definition, and why the hybridization is important. That is important point to explain the shapes of the molecules. Shapes of the molecules. Hybridization is important. Someone will ask you why hybridization is important. You can tell to explain the shapes of the molecule, hybridization is important. And second point is to form equal energetic bonds. To form equal energetic bonds in the covalent molecules. Hybridization is important. Then what is the definition of hybridization? So here I am going to write intermixing of orbitals of an atom will produce same number of hybrid orbitals, which are identical in energy and shape. This phenomenon is called hybridization. A very simple definition, children. That is, intermixing of atomic orbitals will produce hybrid orbitals. So atomic orbitals are giving hybrid orbitals. This phenomenon is called hybridization. So actually we have sp hybridization, sp2 hybridization, sp3 hybridization, sp3d hybridization, sp3d2 hybridization, sp3d3 hybridization. So in the competitive exam, every hybridization purpose they are asking example molecule and as well as bond angle shape. So sp hybridization, the example is BeCl2 molecule, and here the bond angle is 180 and the shape of the molecule is linear. And sp2 Bf3, here BeCl2 is beryllium chloride or dichloride and boron trifluoride, sp2 purpose. And here the bond angle is 120 and shape is trigonal planar. And sp3 CH4 methane, bond angle is 109 degrees 28 minutes, tetrahedral shape or tetrahedral. Next, sp3d PCl5 is the better example, and here the bond angle, sir, 90 and as well as 120 degrees. So phosphorus pentachloride, here the shape is trigonal bipyramidal. And next, sp3d2 SF6 sulfur hexafluoride, and here the bond angles are 180 and as well as 90. So octahedral, shape is octahedral. And sp3d3 purpose, the best example is IF7 iodine heptafluoride, and here the bond angles are 72 degrees and as well as 90, and the shape is pentagonal bipyramidal. So these are the hybridizations, very important for class 10th and intermediate. So how sp hybridization, sp2 hybridization, sp3 and all hybridizations will form, I am going to explain you one by one. So first I am taking sp hybridization. So what is the meaning of sp hybridization? Very simple. Intermixing of one s atomic orbital, one p atomic orbital will give two sp hybrid orbitals. Actually, I want to tell you the hybridization happens central atom in every molecule. Central atom in every molecule. I am underlining in each molecule which one is the central atom. So hybridization happens in every molecule, central atom, and the hybridization is mainly for covalent molecules. So sp hybridization I am talking intermixing of one s and one p orbitals will give you two sp hybrid orbitals. So example is beryllium dichloride. Here the central atom is beryllium. So first you need to write beryllium electron configuration, that is 1s2 2s2. So this electron configuration is called ground state. But the hybridization happens in the excited state. It means in this molecule the central atom beryllium is involving in hybridization and giving hybrid orbitals. But to involve in the hybridization, the beryllium central atom will show excited state. In the excited state only the hybridization will happens. So what is the excited state? Beryllium 1s2 and here the valency shell is 2s. The electron jumps from 2s subshell to next subshell, that is 2p in the beryllium. So 2s2 becomes 2s1 and 2p 1. So this is the excited state of beryllium. So in the excited state you will get unpaired electrons. That unpaired electrons having orbitals intermix. So here 1s 1p intermixing, then you will get two sp hybrid orbitals. Then if I draw the shape of this s and p, you will get like this. This is the s orbital and this is the p orbital. S of beryllium, p of beryllium, then both are going to intermix, then you will get like this. So these are the two sp hybrid orbitals of beryllium. So these sp hybrid orbitals of beryllium going to end overlap with the chlorine's pz orbitals. How? So when you write chlorine atomic number and electron configuration, this is the exact 3s2 3p5. So you need to write orbitals, but I am writing only valency shell 3s2 3p5. So it is px, it is py, it is pz. So in the chlorine, pz orbital is having unpaired electron. Then I am going to take the two sp hybrid orbitals of beryllium. So beryllium two sp hybrid orbitals, each one is having unpaired electrons. Then left side, right side, I will add 1 chlorine's pz orbitals. So this is the pz of chlorine. So another pz of chlorine. Then you are going to get so this is exactly BeCl2. BeCl2 exactly. So this is chlorine pz, this is chlorine pz, and the mid one is beryllium 2sp hybrid orbitals. And here This formation is called sigma spp. They are asking in the examination, when the beryllium 2sp hybrid orbitals end overlap with the chlorine pz orbitals, what type of overlapping it is? So sigma sp is coming from beryllium and p is coming from chlorine. That is why the overlapping is sigma spp. So here the bond angle is 180 degrees and the shape is linear. Then how many sigma bonds are there? 2 sigma bonds are there. Very important. And here next, second one is sp2 hybridization. sp2. So very simple, children. sp2. So in the name the answer is present. 1 s orbital, 2 p orbitals intermix and give you 3 sp2 hybrid orbitals. 1s, 2p. So number of atomic orbitals intermixing 3. Number of hybrid orbitals are forming 3. That is the rule. The best example for sp2 hybridization, bf3. So in the bf3 the central atom is boron. So I am going to write electron configuration 1s2, 2s2, 2p1. So 1s2, 2s2, 2p1. So this is ground state, GST. But if you want to perform hybridization, the central atom should get excited state, that is boron 1s2, 2s1 and as well as 2p2. So 2s1, 2p2. So the intermixing of 1s, 2p will give you 3 sp2 hybrid orbitals. Then how the s and 2p orbitals intermix, I am going to show you. So this is the s spherical shape, s of boron, plus this is px of boron. Then you can take this is py of boron. So intermixing of these 3 atomic orbitals will give you 1, 2, 3 lobes. So splitting is happening here. So this is the 3 sp2 hybrid orbitals of boron. So here s is having 1 electron, p is having 1 electron, nothing but px is having 1 electron, py is having 1 electron. So I can show here 1, here 1, here 1. So 3 sp2 hybrid orbitals are having unpaired electrons 1, 1, 1. So what are the adjacent atoms in the boron trifluoride? Fluorine. So if you write the fluorine atomic number 9 and electron configuration is this. p5. Again px, py, pz. So in the fluorine, pz orbital is having unpaired electrons. But in the bf3, how many fluorines are there? 3. So you need to take 3 pz orbitals which are in dumbbell shape. So first of all I am taking boron 3 sp2 hybrid orbitals, 3 sp2 of boron, then end overlapping with the 3 fluorines pz orbitals. So you can draw anyway dumbbell. So here 3 electrons are there. I am taking anti-clockwise here. Then here the overlapping, end overlapping, I am going to show you for bf3. It is 1 pz of fluorine, it is another pz of fluorine, and it is another pz of fluorine. So electron pair I am keeping, so it is exactly equal to this shape, so which is called trigonal planar. Trigonal planar structure, and the BF3 bond angle is 120. And how many sigma bonds are there? 3 sigma bonds are there, and this overlapping is called sigma sp2 p type overlapping. Sigma sp2 p. sp2 is coming from boron, p is coming from fluorine. So this is about sp2. Next, sp3 hybridization. It is very familiar. sp3 hybridization purpose, the best example, methane, CH4. You can call CNG, you can call fire damp, you can tell marsh gas, many names are there. And here I am going to write the central atom carbon electron configuration, because that can participate in the hybridization. So 1s2, 2s2, 2p2. So 1s2, 2s2, 2p2. So this is ground state. Need to write excited state. 1s2, 2s1, 2p3. So 2s1, 2p3. So the intermixing of 1s, 3p, you will get 4 sp3 hybrid orbitals. So sp3 hybridization is nothing but intermixing of 1s plus 3p orbitals will give you 4 sp3 hybrid orbitals. So I got here 4 sp3 hybrid orbitals, but how the orbitals intermix I am going to show you. This is s of s orbital of carbon plus px of carbon plus py of carbon, pz of carbon. Then these are the 4 lobes. Because 4 atomic orbitals are intermixing, then we will get 4 hybrid orbitals. So the splitting is happening here, 1, 2, 3, and 4 sp3 of carbon. So the electrons are like this, unpaired electrons. Then this 4 sp3 hybrid orbitals of carbon end overlap with 4 hydrogens s orbitals. I am going to show you. These are the 4 sp3 hybrid orbitals of carbon, then 4 hydrogens s orbitals, so s of hydrogen. Then here the overlapping. So here I am going to show you. This is the first hydrogen S, this is the second hydrogen S, this is the third hydrogen S, and this is the fourth hydrogen S. So here you will get electron pairs, and here the overlapping is called sigma sp3s, and it is exactly looking like carbon, hydrogen, 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 hydrogen. So this is the sp3 hybridization, and here the CH4 bond angle is 109 degrees 28 minutes. So tetrahedral shape. So very important for board exams. And next I am going to talk about sp3 dehybridization. sp3 dehybridization. Very simple, children, same like sp, sp2, sp3. Intermixing of 1s plus 3p plus 1d orbitals will produce same number of 5 sp3d hybrid orbitals. This phenomenon is called sp3d hybridization. Then the fine example for this PCl5, phosphorus pentachloride. So it is the good example for expanded octet, or you can call super octet molecule. And here the central atom is phosphorus. I am going to write electron configuration 1s2, 2s2, 2p6, 3s2, 3p3. So just I am writing valency shell, it is 3s2 and it is 3p3, because valency electrons are responsible to form the chemical bonds. So it is ground state, but need to write excited state. Phosphorus 1s2, 2s2, 2p6, 3s. You need to write here 3s1, 3s1, 3p3, 3d1. So 1 electron in the s, 3 electrons in the p, and 1 electron in the d. 1s, 3p, 1d orbitals are intermixing. Then we are going to get 5 sp3d hybrid orbitals. So this 5 sp3d hybrid orbitals end overlap with the chlorine's pz. So in the previously I have given that chlorine atomic number 1s2, 2s2, 2p6, 3s2, 3p5, 17, and valency electrons are 7. To get octet it required only 1 electron. So pz, py, px. Pz is having unpaired electron. So phosphorus 5 sp3d hybrid orbitals end overlap with 5 chlorines pz orbitals. Then how the orbitals overlapping, I am going to show you. So this is 1 and this is 2, 3, 4, 5. When 1s, 3p, 1d orbitals intermix, you will get 5 sp3d hybrid orbitals structure in the above manner. So 5 on nothing but 5 hybrid orbitals are having unpaired electrons like this, and chlorines pz. So 5 chlorines, 5 pz. So pz of chlorine. Then you can expect the overlapping 1, 2, 3, 4, 5. So here I am going to take another color, that is first chlorine pz, second chlorine pz, third chlorine pz, fourth chlorine pz, fifth chlorine pz. And here the overlapping is sigma sp3d p type. So total 5 sigma bonds are there, 5 sigma bonds. Then the structure phosphorus, chlorine, chlorine, 2 chlorines are away due to the repulsions, 3 chlorines are near to the central atom. So this is trigonal bipyramidal shape of PCl5. So here the bond angle is very important, that is here you can write 120 and here you can write 90. So these 3 chlorines are called equatorial chlorines. So equatorial chlorines are 3. Then these two chlorines are called axial. So axial chlorines are 2. Very, very important. They are asking in the examination how many equatorial chlorines and how many axial chlorines. This is the equatorial bond angle. This is the axial bond angle in PCl5. Next, sp3d2, sp3d2 hybridization. So in the name the answer is present. 1s 3p 2d orbitals intermix. These all orbitals are coming from central atom only. So 1s 3p 2d orbitals intermixing and giving you 6 sp3d2 hybrid orbitals. This phenomenon is called sp3d2 hybridization. The best example is SF6 sulfur hexafluoride, and here the sulfur atomic number 16, 1s2 2s2 2p6 3s2 3p4. So it is the ground state. It is going to show sulfur going to show 2 excited states. Very important point. In the PCl5, phosphorus has shown only 1 excited state, but here the sulfur is going to show 2 excited state. So first excited state EST, 1s2 2s2 2p6 3s2 3p3 3d1. It is the first excited state. Then second excited state, sulfur 16, 1s2 2s2 2p6 3s1 3p3 3d2. So I am writing valency shell orbitals 3s1 3p3 3d2. So just the intermixing of 1s 3p 2d 6 sp3 d2 hybrid orbitals we are getting here, and this 6 sp3d2 hybrid orbitals of sulfur end and overlap with the fluorine's pz orbitals, because fluorine atomic number 9, 1s2 2s2 2p5. So unpaired electron is present in the fluorine valence shell pz orbital. So this is pz. So 6 sp3d2 hybrid orbitals of sulfur end and overlap with the fluorine's pz orbitals. So how the intermixing of orbitals diagram I am going to give you. So here 1 2 3 4 5 6. So this 6 sp3 d2 hybrid orbitals of sulfur, so having unpaired electrons and overlap with 6 fluorines pz orbitals. So this is pz of fluorine. Then you can guess the overlapping 1 2 3 4 5 6. So here first pz of fluorine, second pz of fluorine, third pz of fluorine, fourth pz of fluorine, fifth pz of fluorine, sixth pz of fluorine. So exactly it looks like sulfur, fluorine, 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 and here 2 fluorines are away, axial fluorines. So this is octahedral shape of sulfur hexafluoride. It is a super octet molecule. superoctet molecule. So here the bond angle is 180 and here the bond angle is 90. Very, very important. And here the overlapping is called sigma sp3d2p. And last but not least, that is sp3d3 hybridization. sp3d3 hybridization, the exemplary molecule is IF7, iodine heptafluoride. Very, very, very important. And here the iodine is the central atom, its atomic number is 53. So here electron configuration is 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, then 4p6, 5s2, then you can count here 2 plus 2, 4, 10, 12, 18, 20, 30, 36, 38 dps, then 4d 10, 5p 5. You can count here up to here 30, 36, 38, 48, 53. So valency shell is this 5s2 5p5, 7 electrons, because it is halogen, 7th A group element, 7 valency electrons. So iodine will show 3 excited states. They are asking in the examination. In the IF7, central atom is iodine. To form the hybridization sp3d3, how many excited states shown by iodine? So just you remember 3 excited states. So 7 orbitals intermix, 1s, 3p, 3d, and you will get 7 sp3d2 hybrid orbitals. And the structure I am going to show you here: iodine, fluorine, 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 and this is the structure of iodine heptafluoride. It is called pentagonal bipyramidal. Shape, and here the bond angle is 90 and here the bond angle is 72. So you need to remember in the F7 2 axial fluorines are there and 5 equatorial fluorines are there. In the IF7 5 equatorial fluorines and 2 axial fluorines, and at the same time in the SF6 4 equatorial fluorines, 2 axial fluorines. So this is what hybridization in my term. I hope you got it. Thank you.